So let us continue with the last slides of the second lecture. So we didn't have time to cover contact modeling. All right. Regarding the test, we will speak about it in the beginning of the second lecture that we'll have today. So if you didn't answer the question yet, you will have time to do this, right? Okay, so last two lectures were devoted to the basic understanding what is the difference between analytical modeling and simulation. And we considered modeling of a mass spring damper system. And once again, it will be your first practice task to do basically the same, but you will have more complex system. So it will be look like not a one mass with one spring and one damper, but it will be two mass system, and there will be different variants with the translation motion and with the rotation motion. But basically what you have to do is to derive an Euler-Lagrange equation symbolically. Then you need to create a simulation model using basic Simulink blocks, and then to do the same using Simscape blocks. And the results must be the same. If the results are the same, it means that you have done everything correct. Okay, it's like a small recap of the first and the second lectures. And we stopped right here. Okay, so contact modeling. Why do we care contact modeling? Why do you think? Pressure and grasping, grasping forces. What else? We can walk because of friction. Car is able to drive because of the friction, and without the friction, world will be the different place. Right? Sure. Yeah. Maybe more examples. Legit robots. Legit robots. Sure. So you mentioned manipulative robots, locomotion robots, but also when we study just mechanisms, we also need to model contacts. And basically, when we want to tackle a problem to create a robot that interacts with the world, we need to consider contact modeling. And the main feature here, the important part here, that contact modeling and physics of contact, those are two different ways how can you take a look at the contact. For example, if I have an object, and if I drop it on the ground, all the kinetic energy and potential energy and kinetic energy will be transformed into heat, right? When an object hits the ground, we have a lot of different energies and deformation. We can talk about stress and strain. We can talk about the elastic and plastic deformation of an object and in an environment. So there is a lot of going on there in the real physics. But the way how we do contact modeling pretty different from this aspect, because if we'll do the modeling of all energy transformation, it will be just too complex. And when we use modeling, for example, in order to use reinforcement learning to learn how to walk for a legit robot, for example, it will be just too expensive for us, I mean, from computation point of view, to model the contact from energy point. All right, so the way how we do contact a little bit different. Actually, there are a lot of different models, but beyond them, there is the most popular, and it's called penalty-based approach, and we will going to tackle this kind of approach because MATLAB used the same method. If you'll do modeling in different kind of simulation packages, for example, if you want to use free open source project, you can use Python with the different simulators such as Bullet or Chrono or Mojoko, you will have a lot of different ways to model contact. But we're not going to cover all of them. We will cover just one of them, which is called penalty-based. So the idea is the following. That we model interaction between objects. It's like there is a normal force and there is a friction force, according to the picture that we have right here, right? So we have normal force, we have a friction force. And we need to somehow derive an equation for them. How do we model normal force? In order to model normal force, we think like there is a spring between an object and another object. But this spring generates force only when contact takes place. So we assume the following. Let's assume that it is an object. It's like a ball and a ground. When the distance here, the distance is greater than 0, there is no contact, right? It's pretty obvious. But if the distance equal to 0, it is a contact, right? But clearly, here the distance between an object and a ground equals to the 0. And the moment when this marker hits the ground, also the distance equal to 0. But forces must be different, right? And taking in mind that it will be just too computationally difficult task to model all the energy transformation, we do the trick. We assume, and by the way, in order to make the simulation easier from computation point of view, we think that actually all bodies are rigid. Do you know what means rigid? Yes, it means that if we will take two arbitrary points, the distance between them will be constant. It means rigid. So in order to model impact, we do the trick. We assume that bodies are overlapping. So there is a penetration, one object into another object. And this penetration, it's like delta x, or right here I call it delta. It's a penetration. It's like the distance that measures how one object penetrates another object, and this is the way how we can model deformation of actually rigid body, because we know that all the bodies actually not rigid. Rigidity is just an abstraction as a way of simplification of physics, but in order to represent this feature of deformation in our model, we do the following. So we think like there is a penetration, and it's supposed to be pretty small. You know, if we want to model like a steel ball falling concrete, this penetration must be less than 0.01% of the dimensions, I guess. And actually, in order to model the force, we need to multiply the penetration with coefficient of stiffness. And it's not something physical, it's just a parameter for our model. There is no such a thing like coefficient of stiffness in the real world. In real world, we have Young's modulus, we have shear modulus, we have Poisson ratio, all of this stuff. But right here, in order to make it simpler, we use just linear relation. In real life, it is non-linear, but we're using a linear model to represent it. So the force reaction forces right here will be penetration times coefficient of stiffness plus it is like a spring force and damping force, just like we already covered in spring mass damper system. We multiply the derivative, time derivative of this penetration times coefficient of damping. There I use Kc and that is it doesn't matter. It means that there is penetration, derivative of penetration, coefficient of stiffness, and coefficient of damping of this penetration. And it's not like you can find those parameters in a book, because it has nothing to do with the physics. It's just our task to find such parameters that make sense. It means like if we model, and you can actually try to do this at home, you can model how 1 kilogram body hits the ground, and if you choose here like 1, 2 billions like this, it will give you penetration really small, but also the force will be like several tons, and it's clearly cannot happen when you drop ball, 1 kilogram ball from 1 meter, for example. So the force, the plot for the force times force and in relation of time will look like this. For example, this is 0. Here it hits the ground, the force will be 0, then it hits the ground, and then it will be like 10 newtons for the rest of the time. So, and it can go into infinity since it depends on your coefficients.
I wanted to ask about this. Shouldn't we add a constant term to the normal force to represent this mg part?
No.
Because here Kc delta plus vector c delta dot, and after this small moment will be 0. But the normal force will be 10 newtons.
You can try it at home to do this. You can actually try, and you will see that when will rest in the, it will go into the rest position. The magnitude of this force will be exactly as mj, since it will the system will be in the rest state. Rest, it means that the sum of the forces must be equal to 0, so it will be like force plus mj equal to 0, and right here the magnitude will be the same, the direction will be different.
So delta won't be 0.
Delta will not be 0. It will be almost 0. I mean, numerically it will be 0.00000, and eventually 1. But it won't be 0, because otherwise force will be 0. And the delta depends on those coefficients. If you want them to be almost 0, it means asymptotically tends to 0, you need to choose very high coefficients, but it will lead you to very high forces. If you want to consider that your bodies are elastic, they can deform, and you want to get lesser value for forces, you need to use lesser coefficients of here. So it's something that you need just to tune on your own. All right. Is it clear? I hope so. All right. It's just one point that we have normal force, but also we have friction force. And the trivial way to model friction force, it just the relation between velocity and some coefficient, friction, just as we had it for the damping force, because damping it's the same friction. It's just the force that sucks energy, right? It's dissipate energy. But also there are models that are not non-linear, because the multiplication of coefficient of damping times velocity is linear model. But also we can use non-linear model, and it's something that you can see here. But let me explain you what it means. So let's assume that you have a body like this, and it doesn't stick like, okay. And I want to apply force in order to force this body to move. And in very first moment of time, initial moment of time, I need to apply more force than I need in second moment. And this is why the plot looked like this. So here is the friction force. It is velocity. And right here, in order to make body to move, I need to apply more force than is needed then. So it looks like this. So and this portion of force is called breakaway force. This one is F breakaway. And then it will be a little bit smaller. But then it depends on the viscosity, and it could look like this. And the angle here depends on the viscosity effect. And if we'll go into opposite direction, it's pretty much the same like this. And it's called Coulomb model for friction force. So breakaway, viscosity friction, Coulomb friction, and actually, since we're using MATLAB, we can just use documentation. Let's us find a block that models friction. Because MATLAB is the great tool because of the documentation. I mean that other packages, simulation packages, may be better in terms of efficiency of computation and speed of computation, but it does not have such great documentation. Okay, so here you can see that there is a block which is called translation friction, rotation friction. We can choose friction, translation friction, and here you can see pretty much the same picture. So I took it from here, but also you can see the whole description how these blocks works, and also an equation that computes the force. And actually, in order to compute it, you need several parameters, but all of them depends on each other, and it leads to the fact that we actually need to use just a static component and a dynamic component, and all other components will be computed out of those. For example, let me open the example that I showed you previously for the mass and spring damper. Okay. For example, here it is not spring, but I can add here friction. Library link, go to library block, and here friction. So here you can see that you need to write down breakaway friction force, that one. Breakaway friction velocity, it depends on the viscosity effect. Coulomb friction force, and once again viscous friction coefficient. And those parameters already you can find in the book, because it's about physics. It's something that you need just to find out for the object that you want to model. It's like rubber and steel, concrete and wood, plastic and plastic, all this stuff. Or you can measure by yourself, because it's pretty simple how to compute them. All right, let us continue with our slides. Where is it? So let us consider an example of the system. So we have a mass that hits the wall. So pretty much the same example that we had previously, but here we have not a damping force, we have friction force. And actually slide can be misleading, because right here I wrote that it is a friction force, but actually, and right here I use a non-linear component, so actually I need to fix it in this slide. It will be better to understand. So the idea is the following. We need to apply force to a body only, I mean normal force, only when it hits the ground. And right here it's not the ground, it's wall. And we need to apply it only there. So here you can see a Simulink model. So let us consider this system. So the equation will be, the right equation will be the following. So total force equal to minus normal force, let me use N for normal force, minus friction, and minus spring, friction, normal force, like this. Is it clear? Okay. So now let us take a look at this schematic representation, half of it in Russian, most of the letters, but I think it's not a big deal. Oops. So if we divide force by the mass, we will take an acceleration, x double dot. If we, just as we had it in previous example, if we integrate acceleration, we will have velocity. If we integrate it once again, we have position. All right. If we multiply position with the coefficient of stiffness, you will get force. So this is the stiffness of spring, and this is the force which is generated in spring. All right. Then, right here, we can use the equation that I just showed you in the Simulink. But in this particular example, I used even simpler model. I have used here a lookup table. It means that if we already have a plot like this, we can feed it with the velocity, and it gives us as an output the force. And right here, this block computes the friction force. All right. And now how can we compute the normal force of interaction? I use the following. So we need to measure the distance between an object and between the obstacle, right? So here, its measure 0 indicates where is the obstacle, and this line represents position, I mean deflection. It's not delta yet, I mean it's D, this D, but delta is already penetration. Right now it's D. It's multiplied with the coefficient of stiffness, velocity multiplied with the damping, and we composed this equation, but in this particular schematic representation, it's not delta, but d. But right here, you can see a switch block. It means that we apply it only when d is less than, when it's negative. And then d becomes delta. It becomes penetration. And we apply force only when the mass hits the wall and go inside it. Okay? So now let me find this model. I think I found it. Yeah, great. And here it's in English. So here you can see the right equation. Springs per force, by the way, minus, it's the matter of sign, matter of direction. So we would have total force divided by mass, acceleration, velocity, position. All of this is pretty obvious. About the lookup table. So here in MATLAB we have a block which is called a lookup table, and we need just feed it with the relation. So here you can see the plot that looks like the column friction models, and it means that if I have x velocity out of this function, I can get friction force. Normal force here, x multiplied with the coefficient of stiffness, and you can see that it's 10 in power 6, so it's pretty huge. And damping is pretty small. Penalty force, why it's called penalty base? Because of this penalty force, which force an object goes in opposite direction. All right, why did I want to show you the actual simulation? So if I run it, right here you will see position and velocity. Position is the distance between along the x, right? So it's like it's supposed to look like this. It's a wall. It's our object. We stretched the spring and just hold it, right? And it's just bounce like this. So you have a plot for the position and velocity, but let's take at the numbers below 0. And here it's not very good like this. And here you will see, you have to see that yellow line, we have negative values below 0. Can you see it? And each time when it hits the wall, it's lesser. Why is it lesser? Because of the damping component, because it loses energy and the force of interaction is less. All right? What do you think will happen if we'll choose very small coefficients? It will penetrate inside object. And this is why you need to choose the proper coefficients, such as your object collides, not just go inside each other. Okay. Is it clear, the idea? But still, it's pretty simple model of 1D system in real life, we have spatial motion with 8 coordinates. It's like x, y, and z, yaw, pitch, and roll. And real model, little bit different. I mean, it's just more complex, but the whole idea is the same. For example, if we'll take a look at the model of contact library, which is you can find in MATLAB, and you can open the mask, and you will see how huge, big, and complex it is. But still, the idea is the same. All right. So here I just have the same plots. And here I have just animation of a ball which is falling on the ground. I mean, right here, I just showed you model that been composed out of just basic Simulink blocks, but also we can do the same using 1D Simscape blocks and using Simscape multibody. And we're going to use the Simscape multibody, and I will tell you all about a little bit later. But here you can see just how simple it is. I mean, all the math is inside. All right. Right here, it's just for an extra. You can see contact modeling that been constructed using bond graphs. And the idea is the same. For example, on the left you have one object, and on the right you have another object. SF, it means source of flow, source of velocity here. So it's the way how can model ground. 1, it means the velocity is constant, right? If you integrate it, you will have what? Position. So you have integration plus and minus. It allows us to compute delta, the difference between positions. It will be the delta, and condition, it's just the same switch blocks that mean that works like we apply force only when the distance is negative. And XO is just another block for the condition. And RC is a damper and stiffness. So in R and C, you put your damping coefficient and stiffness coefficient. The idea is the same. But still, it's just 1D example. All right. So also I put here reading. And for those who interested in more details, and for those who want to pass an exam, the reading is a must. That's it with the material of the second lecture. And now we can go to the topic of today's lesson.